We found it. Okay, service announcement. We found a passport. Now I need my reading glasses because it's too small. Thank you so much for the test. For Robert Lange ou Lange. It's you? Thank you. Congratulations. And thanks for the lady. So, let's start. If we start on time, we finish on time, and we will get some probability to get some leftover for the lunch, right? Because lunch happens mostly during this. And by the way, there will be leftover, right? I mean, the buffet will still be open, so no worries. Thank you as well for welcoming you here, and thanks for attending. I understand that the agenda for V6 is kind of bad today, because you get 2 level 3 sessions that are very interesting about IPv6. One about IPv6 routing by my friend Peter, and this one, which is also interesting, I hope. So it's basically about IPv6 security in what we call the first hop. The first hop is really between the client and their default router. This is the first hop. We will talk about, of course, all the switch on the path. When I look in the room, I saw some familiar faces. So how many of you have been with my session either on Monday or Tuesday? Okay, so you were not afraid to come back, which is cool. For the others, you are of course welcome. And I will ask the question just for the people who were not in my session. Okay, so for the newcomers, let's say. For the newcomers in my session, who runs IPv6 currently? Oh, cool. And for the people in the room who did not raise your hand, neither in my session or I am not running IPv6, you are either a liar, right, or really, really mistaken. Because if you think about it, and liar is between double quotes, of course, right? If you think about it, what defines an IPv6 network? It's not an IPv6 radio, wireless LAN controller or router with an IPv6 logo on it. No. What defines an IPv6 network is any network, Wi-Fi, Ethernet, whatever, having 2 hosts doing IPv6. So, and we all know all the Windows, the iOS, the macOS, the Linux are having IPv6 enabled by default. All of them have got the link local addresses, FE80 something. So on your IPv4 only network, 2 machines, 2 phones having V6 can communicate over the FE80 address, the link local. So all of us in this room are running IPv6 network. Most probably you know it, right? But it also means that if you do not secure this semi-hidden IPv6 network of yours, you may be in deep trouble. And the first of security is basically really the first level of security here. Okay. Like usual, there is a WebEx room. Feel free to ask questions, either very specific to you or generic. I will reply, of course, not now, right? I'm speaking, but I will reply later today and the week after. Feel free. In my other session, questions are still coming since Monday and Tuesday, and reply and answer, of course. But I really welcome, it's kind of a small room. I see everyone in the room. If you have a question that you think is useful for everyone, raise your hand and shout, and then ask the question. As you can guess with my Dutch last name and my French accent, I am from Belgium. Belgium is well known for chocolates and beer. So I bring some chocolate for good questions, or actually any questions. Okay? I could have bring beers, but typically the chocolate I throw them. But throwing a bottle of beer, yeah, I mean, except for the first row, it's not really useful. Anyway, having said this, Session objective. As you know by now, there are three big differences between IPv4 and IPv6. Larger address space is not really a concern for this session. The link between the IPv6 address and the link layer, neighbor discovery, replacing ARP. This is the second one, big focus here. And the third one are extension headers. We will talk about extension header here as well. Be warned, I will not explain again what is a route advertisement, neighbor discovery, and so on. I mean, I will make some quick refresh, but it will be 10 seconds. Transition. And I talk about transition to IPv6 and not migration. You know the story, right? Migration are for birds. During winter, they fly south, but in spring, they come back. I don't want immigration to IPv6 for one winter, and during the summer coming back to IPv4, right? So it's transition. So, transition again. At my first job, this is what I was driving. Nowadays, I rent plane because they are too expensive, and I fly them. Pretty cool. Now, when I started my job, we were running multiple protocol network. DECnet, IPv4, I mean, no IPv6 at that point of time, XNS, ChaosNet, and so on and so on. Multiple stack. And one protocol was DECnet phase 4, with addresses like 1.100 at the layer 3, which was mapping at the layer 2 with 4 bytes always the same, and the 2 trailing bytes, basically the layer 3 address. So the layer 3 address was hard-coded into the layer 2. No need for ARP or neighbor discovery. And now, moving to V6. This address ending with 1, 2, 3, 4, 5, 6. This is the layer 3. If I want to know the Ethernet address associated to this one, and this is the focus of this talk, which is the reason why I'm explaining this. We are sending a neighbor solicitation to a specific multicast address. ARP was broadcast, right? But here we multicast. And the multicast address is also 104 bits hard-coded, always the same, FF02, ending with 24 bits of the V6 layer 3 address. But this is a layer 3 multicast. How do I do the mapping now between the layer 3 multicast to the Ethernet or layer 2 multicast? Same thing as I did nearly 40 years ago now, shame. 3 bytes hard-coded and the 24 bits. So I find it striking to come back, right? Kind of a circle in my life. Took me 85 hours of supervised, so with a flight instructor next to me and here, I mean, we are not yet there, right? Not every network is already running IPv6, except again for the FE80, right? Because this traffic is done for your FE80. I like to learn stuff, learn flying, learning about IPv6. And what's important is not only to have fun in testing new stuff, but doing it securely, both in the plane and in operating network. And this session is about this. Agenda, Slack, and the route advertisement. These are the biggest issue for many, many years. How to secure this. Next step, as soon as you have your router installed and the default route installed, how to prevent somebody from spoofing your address. So what about the integrity between the layer 3 address and the MAC address? Right? Address availability. Be sure that whatever system you are using, like DHCP, for address availability, is always running. That nobody can block DHCP or can block Slack. Some more information about what we call in Cisco first hop security. This is all the mitigation technique. And by the way, I hope you are running in your IPv4 network something called DHCP inspection, dynamic inspection, who do the same thing, right? It's preventing somebody from stealing an IPv4 address and a MAC address binding. The technique, first hop security, is of course mainly designed in the beginning for switches and routers. But if we go to SD access, which is basically a switch which is distributed over an underlay, it works the same. And some summary. As I said there, in the range, a lot of things that you will see also applies for IPv4. Securing Slack. You know, right? If you were there Monday, Tuesday, you've seen this slide. Quickly on this. People, all your phone and laptop are sending router solicitation. As soon as there is a router, that replies with a router advertisement. The router advertisement contains the prefix, some flags. It allows the client receiving the router advertisement to build up its global address using the 64-bit of the prefix and an interface ID being random or based on the MAC address. He got its layer 3 address. He knows the MAC address of the router. He can send the traffic. Cool. Router advertisements are without any authentication, pretty much like the HTTP4. And 20 years ago, there was an issue with IPv4. There were people configuring on a Windows server, not the HTTP client, but the HTTP server, right? Sending wrong DHCP-v4 information, and you were losing a complete LAN. It's fixed now with the HTTP guard and the same. Guess what? Same thing here. A bad guy can go, black hat, right? No surprise. He sends a router advertisement, what we call a rogue, a malicious, a malevolent one. The client then, oh, why not? I take it. Take the 64-bit, make my interface ID, sending all my traffic, v6 traffic, to the bad guy. And remember, all operating systems prefer usually IPv6 to IPv4, right? And then the guy can do a DOS, receive the v6 packets and do nothing, or run a man-in-the-middle attack. Okay, nowadays with TLS, you will get a certificate issue. That's better, but still, not everyone is using TLS-based or quick-based connection. And again, this attack can be mounted on an IPv4-only network. In my hotel, I ran this attack 2 days ago. It was successful. I mean, honestly, I will explain and show you the packets I'm using it, but it was running in 2026. I mean, I'm lost, right? But anyway, I will not say the hotel name, though. Just follow me after the party, the celebration later tonight to see in which hotel I am. It was a big issue. I am starting doing this presentation, right, around 2010. And I was there. The presentation was much smaller because it basically stopped here. And all the other slides were not existing. What you can do, something isolation mode. So isolate all the clients to each other. So meaning that any clients cannot talk, cannot send a frame, a Wi-Fi or an Ethernet frame, like AP isolation mode or 1 VLAN per customer if you are a service provider. And then when the router got an exception or something called private VLAN, right, in iOS, router advertisement, yeah, this port is allowed to multicast, to broadcast traffic. So yeah, I am sending the router advertisement everywhere. Cool. The bad guy wants to send this rogue array. That's what we call isolated port. It's blocked. Okay. there are variations of the technique there, right? The picture is about private VLAN, but as I said, there are AP isolation mode or others. Excellent, it works fine. But there is caveats. If you prevent communication between the host, how can you print to the attached printer, right? If there are two phones, how can you talk to each other? I mean, there are NDP proxies, of course, go to the router and back. Not cool. What about that? Duplicate address detection. I will come back somehow later, but you need to prevent two hosts having the same IPv6 address. If they cannot check to each other by using that, yeah, you can end up with duplicate address. So it was not good. Next one, yeah. Router advertisement is a plain IPv6 packet, ICMP1. So you can use an access control list very easily, apply the access control list to the port towards the client, but not on the port to the router. And by the way, something important here. You are the network operator. Your switch's access point has physical security. I hope they are not in the corridors, right? It's protected. And you know on which port is the router or the upstream. You have a knowledge and a power which is much better than the attacker. So you know where to deploy the ACL and where not to deploy. In this case, you don't deploy it to the interface on the router, no ACL, array is forwarded, and then you get the story. The guy trying to send a rogue array hit the access control list, packet dropped, and we are safe. Right. Good point here is that still works because that uses a different ICMP type, right? This is a neighbor solicitation and not a router advertisement. Here comes extension headers. And same slide for the people that were there on Monday, Tuesday. For the three next slides are identical. So, quick refresh. Extension headers, each of them has got 2 bytes. One is next header, explaining what's after, and one which is header length, which is the length of it. So, let's start with the v6 header, 40 bytes. There, I put next header equals 0. 0 means the next is hop by hop. Within the hop by hop, I see next header 43, header length 32. 43 means routing, for instance, SRv6. Next header 60, header length 256, 60 is destination. In destination, I could put next header 58, and 58 is ICMP. And in the ICMP, I got 1 byte indicating type 134, which means router advertisement, right? And the numbers themselves is not really important. Now, what about access control list? And specifically, access control list in a switch or in a router. Not in the firewall, right? Firewall is a different beast. Okay, their job was easy before in IPv4. 20 bytes IPv4 and then ICMP directly after. So you were looking for the ICMP type at a fixed offset from the start of the packet. It's no more the case here, right? Because you may have extension headers. Extension headers are not common. I would say 99.99% of the traffic, IPv6 traffic, is no extension headers. But they are valid packets. So, as every extension headers has got the length, I mean, hardware or software can simply go and follow the chain of extension headers until finding the ICMP and type 134. And if there is a deny for router advertisement, like the access list we've seen before, all is good. Hey. Fragmentation. Fragmentation was bad in IPv4. It was already used to evade some access control list. But what if now we take this IP packet, right, and we fragment it in two? So now my route advertisement is split into fragments. For some reason, we need to repeat the hop by hop and the routing, simply because if you fragment a packet into fragments, you want them to follow the same path so they arrive in the right order. And hop by hop is sometimes used for quality of service or telemetry, and you want to have the same quality of service and same telemetry for the two fragments, right? This is the reasoning behind it. Anyway, so we got two fragments. So far, so good. And I fragment it inside the destination option header. Remember though, the next header and the header length are in the first bytes. So they will be in the first fragment. So if you are a firewall again, stateful, or a host, no problem, you do reassembly, and then you do the access control list. If you use the port access control list on a switch, right, they are not stateful, right? They analyze the first fragments, and typically the first fragments always go through. There is indeed, it knows after destination, this is ICMP, right, next to the 58, and the length, but it cannot reach the ICMP because ICMP is in the second fragment. Okay, 1 nanosecond later, second fragment arrives at the switch. And the switch can go, yeah, I know the length of hop by hop, know the length of routing, I know the length of fragment. What is the length of the remaining part of destination header? The total length is in the first fragment, and the length of the first fragment is in the first fragment. I cannot do the math. And even worse, as the next header, 58, was in the first fragment, I have no clue whether it's ICMP or TCP or UDP or ESP, for instance. I am lost, right? I cannot detect it's a route advertisement. Boom. So all my nice feature of access control list to the bin. And it was the situation around 2013 or something like that. Then came this RFC, 6980. Nodes, so the Windows, the Mac OS, right? Receiving NDP, so neighbor advertisement, but typically route advertisement as well, which is fragmented, must be dropped and ignored. Okay. Later, RFC 8200 made it more generic. 8200 is basically the IPv6 standards one. It's the first fragment, remember the one before, does not contain the transport layer with the ports or the ICMP code. It should be dropped. Making then IO-based switch can have two keywords about fragments. Fragment keyword matching every non-initial fragments, and something called undetermined transport, which can basically drop the first fragment. Some more explanation in one slide. So no, IPv6 fragments is no more the end of the world. We have tools, right, to prevent them. And on Monday, somebody told me, Eric, are you sure that 6980 is implemented by all the hosts? I said yes. He told me no. I've tested it. I've retested it in my hotel, and it's indeed blocked by all the hosts. Right? So 6980 is implemented in Windows, Mac, iOS, and so on and so on. So we are safe. Right? The access control list will not be able to drop this weird packet, but the host will ignore it. Right? So that's basically the same. There is some traffic, but who cares? And you can as well use this undetermined transport if you want. More on fragmentation and iOS keywords. So fragments, keywords, deny permit is basically the same as an IPv4. Non-initial fragments. Now, I put a blue book on the top right because that's kind of a tricky thing. Undetermined transport, not on all platforms, right, to be sure. But it matches. You can use it, and the explanation is quite convoluted, right? It's only for deny. You cannot say permit undetermined transport. Doesn't make any sense, right? Would you explicitly permit an illegal packet? So it's a deny only. And that's not match. So it will allow initial fragments. And if you have TCP and UDP into the first fragment, that's also okay, and so on and so on. So this is the description. Honestly, it took me 2-3 minutes to fully understand it. So there's a reason why I put the blue book on the top. This is for later tonight. We made things simpler. Rather than defining an explicit ACL, we use a feature now called array guard. The syntax here will be explained in a couple of slides, and there will be a demonstration. But typically, you have different device role, host and router, right? Typically, you can guess router can send router advertisement, and host cannot send router advertisement. You define policies, and you attach policies, one for the VLAN, which is host, and one more specific to the interface of the router. Okay? And this is basically orange policies are the orange dot, and the router policies are the yellow dot attached to the switch. Now, the router sends a router advertisement. It hits device role router, right? It sends the array everywhere. The bad guy is sending router advertisement. Hit the policy host. It's dropped. Very similar to the ACL, and actually the hardware does the same thing, but it's easier to deploy, right? It's nicer. That's it. I promise you some explanation about the syntax, what you call all the first stop. Every first stop features, the one we do like array guard, but the one that we'll be defining later, you can apply it globally to all the set of VLAN and all the set of interfaces. And you can deploy it per VLAN or per interface. For instance, on this one, I deploy host policy on the VLAN 100, and a more specific one, router, on Internet 00, and device tracking without any word. Policy name means default policy name. I deployed on the VLAN. So what does it mean? Two policies, right, host and router. Packet received on Ethernet 0, as I have a very specific policy attached to the interface, it will trigger this one. So it will select interface Ethernet 00 policies and the policy router. Packet received on other ports on VLAN 100, but not on Ethernet 00. Guess what? It will not apply the specific policies, of course, but the more generic one that we define for VLAN 100. Very easy. This one is basically for your other education. Device role. In the policy, you can define which role is a device. Host, which is the default. The host will receive array from valid routers. It will not receive router solicitation because we know there is no router there. So there's no point to send router solicitation. And all the array received on this port will be dropped, what we've seen. Router, device role router, it will receive all the router solicitation and is allowed to send router advertisement. Two other ones are more specific. One is monitor. If you want to put a Wireshark to see what's happening in your network, this is basically the garbage bin. You will receive all the array and all the RS. So you can run something and see what's happening in your network. Switch, This is between inter-switch link, trunking ports or whatever, where basically all the traffic you receive from the other switch, you assume the switch is also configured array guard, so you are trusting everything you are receiving from this switch. And everything it's trusted, you send it to the other switch. Okay? That's how you can grow a large access layer. We will see as well later device tracking, which is for the mapping between MAC and IP address. 2 device role only, no the default. So we are inspecting all the neighbor discovery messages, what we call gleaning, to gather the information. And we guaranteed that only valid neighbor advertisement and route advertisement are sent. And switch is the same. Right? We are trusting the other part. Demo time. So, a very specific demonstration. I use Cisco routers because it's easier for me. A switch in the middle, a router that will send route advertisement. There's a good one. It will send Cafe Babe, 2001 DB8 Cafe, a host, which is also the victim, and a VLAN, the bad guy. If I look at the host and its interface to the switch, we see here. I receive a prefix DB8 Cafe, and I make up my EU64 IPv6 address. Which kind of routers do I have attached and discovered? Only one, coming with an easy to remember link local, FE80:1. But it's default setting. So preference is medium. That's how iOS routers are sending it. It can be low, medium, or high. Priority, basically. Go to the bad guy. And VLAN is interesting because there's the same word in French as in English. So we need to enable VLAN as a router. We do it. Okay, IPv6 unicast routing. Yeah, there was some debug message, but you don't care. Another very specific prefix, DB8 bad. I am a bad guy. I set high preference, so I'll be selected. Look about the lifetime. They are in seconds, because I don't want to wait hours, right, to clear the cache. Back to the host. If I look now at the interface, look, I've got 2 v6 addresses, including one from the bad prefix, right? And then I use bad, which is easy, and still the good one. Normal, right? I'm naive. I'm trusting everything. If I look about the routers I've received, I got 2 of them now. One coming from the bad link local, again, easy to remember, preference high, and the good old one, FE80:1, preference medium. So guess what? The router, the host, is selected the bad guy as the default router, and it will send all the v6 traffic, basically, to this bad guy. Okay, not good. Let's be modern. Go to the switch, and again, we know where the router is and where the clients are. We can enforce this and use this knowledge. I will define a policy host, device role host, right, like in the previous slide. So only receiving valid arrays, blocking arrays from this host. Define policy router. I can send array, and I will be receiving arrays. So far, so good. I need now to apply specific router policies to the port where the router is. And guess what? On the VLAN, I will basically attach the policy node. Back to the host. And again, I use a very short timer, right? So all the prefix is expired. The bad one. Routers, only one, right? The bad guy, FE80 bad, has disappeared, expired. No more there. And we are using the right prefix, which is cool. Look at the interface. Only one prefix, the good one, cafe. Okay? The other one is expired, because I use, again, very short timer. And it will take hours for the demonstration. If I go on the switch, and I enable debugging to see what's happening, again, short timer, right? So the array are coming quite fast. So I stop the debugging. Look at this. It's coming from the bad link local, but also the bad interface. I drop. There's the reason why the host doesn't receive it, and timeout. The good one received from the right interface with the right link local are not dropped. So it works. And that's it. Works perfectly fine. Remember, you need to do this on your IPv4 only network, right? Meraki, for the radio, the access point, has got array guard enabled by default, which is cool. They can do it because they know where the router is. The router is never on the Wi-Fi side, right? It's on the uplink side. So that's easy. For the switches, same thing. Now, this is what I did in my hotel. Wireshark. First thing is the router advertisement. A rogue one, right? Sent by myself, right? But the hotel is mostly packed with Cisco people, so it was not too bad. I was using, if you look at here, DB8 dead. So the prefix I was advertising is 2001 DB8 dead. If you look about it, I was not pretending to be a real default router. If you second read it, router lifetime 0, meaning I'm not a router. If I would have been the bad guy, I would put a timer, which is not 0. And the other timer for the prefix is 6 seconds, which is the bare minimum. Okay? So in the worst case, I was introducing bad IPv6 addresses for 6 seconds. And now look about it below. You see neighbor solicitation for 2001 DB8 dead. So why other hosts in the hotel were sending neighbor solicitation for one chocolate? Duplicate address detection, yeah. I still have 11 chocolates, right? So yeah, I got, in this case, more than 100 hosts doing this. And somebody told me, yeah, Eric, if you fragment the router advertisement, it will go through and the host ignore RSC 6980. I did it later. Yeah, I was indeed seeing the router advertisement in 2 fragments, but no neighbor solicitations, so they were all refused, right? So the hosts are protected. Okay, integrity of MAC and IP. Let's a quick refresh. Remember, this is, you do neighbor solicitation, neighbor advertisement, right? And something which is cool, when you do a neighbor solicitation, you may have an option telling, hey, my own MAC address is this one, right? It's an improvement as opposed to ARP. There are also 3 flags into the neighbor advertisement. Router, saying that the sender is a router, not really important here. Something which is very important is the S, solicited. It's whether the neighbor advertisement is a reply to a neighbor solicitation or it's a spontaneous neighbor advertisement in case you change your MAC address, for instance. An override is basically overwrite an entry in my neighbor cache. The state in the neighbor cache is a little bit more complex than the one for IPv4 and ARP. You start with incomplete. You create an entry, IPv6 address, blah, blah, MAC address, basically unknown, incomplete. And then you send neighbor solicitation. As soon as you receive a neighbor advertisement, you move in reachable. And you use it for a couple of seconds, right? Typically minutes even. As long as you receive traffic from the other peer, you keep this counter running, right? So you reset the counter to 0, that's not expired. Now when it's closed, you don't receive traffic for some amount of time, you move to the state stall, right? Your address is stolen. You still use it though, right? But you kind of being, yeah, I'm not so sure about it. If another timer expires, you go into the probe. This is where you are sending a neighbor solicitation actively, right? And if you don't receive a neighbor advertisement when in the probe state, the entry will come back to incomplete. Right? It's simply to check whether you are still there. Okay, easy one. Again, a quick refresh. A, IP address A, MAC address A, IP address B, MAC address B. I will be sending a neighbor solicitation because I want to talk to B. The ICMP type, you don't care, is 135. The source address is the address of A. The source SLLA, source link layer address, so the MAC address is MAC A. Destination, remember the stuff with the plane and so on. Solicit note multicast, 104 bits all the same, and then the 24 bits. It makes the solicit note multicast B. Target B. Send it, multicast it, right, to the solicit note multicast. And my neighbor cache is incomplete. As I included, A has included its link local address in DNS, it allows B to already create an entry in its own neighbor cache for A. IPv6A is MAC address A, and I will put it in pro because I want to check, really, right? But I already got the int. I reply with a neighbor advertisement using the bit solicited, and then you get the ID. I am becoming reachable. I know that address B is MAC address B, and it's intent reachable. And I can send data. At some point of time, right, data exchange, but stop. So the mapping becomes stalled. Then I will be sending just another neighbor solicitation, so it's called NUD, neighbor unreachable detection, but it's just a plain neighbor solicitation, right? There's no magic there. And while we are doing this, the data is still being exchanged, right? It's stalled, but it's still there, it's valid. I mean, we hope it's valid. Now the gentleman here, B, will send an NA, neighbor advertisement, with the solicited flag, and the entry in the cache becomes reachable again. Now, when it was designed in 96, 97, MAC address were changing sometimes because they were replacing hardware, I don't know. MAC address don't change too much, just beware in my last slide, nowadays. So if MAC address B is changing to MAC address BB, what's happening? It will be sending multicast it to all nodes in the VLAN, FF02:1. A neighbor advertisement with the two flags. I mean, solicited flag will not be there, and the override flag will be here, making all the nodes will update it. Cool. What about signature? Authentication? None, of course, right? Yeah, so you get it, right? So A talks to B, right? Everything is fine. Session is established, but the bad guy is coming, and he's sending this multicast packets, right? A. B now is MAC address C. Okay. I changed the MAC address for B into MAC C, being reachable, and you got it, right? Traffic is going there. It's basically DSNF of 2001 applied to IPv6. Okay, how can we fix this? There is a way. Question? Wait, you are too far. Let me come with a chocolate. So?
You have 2 slides before. before you have the state, probe state, and the delayed state. And what will happen when no traffic is sent, data is sent between the two hosts? Are the neighbors timed out, or what's
So the question about the slide where all the transition I was talking in all the state. So once you are in reachable state, come back on this one. Okay, it becomes stall, right? Because there's no traffic. So far, so good. I am sending a node. If I don't get the reply, it jumps back to incomplete. And then if you restart again to want to connect it, the host will restart from scratch. It's incomplete, so like the slide before, I am sending a neighbor solicitation. Hopefully I got a neighbor advertisement. Most probably not in your case. It doesn't reply. Then it stays there and the connection is cut, right? It's broken. So on this slide, there are 3 different hosts, H1, H2, H3. And the switch in the middle will be building a device tracking table, which is basically the mapping between addresses, MAC addresses, VLAN, and interface. And from the top to the bottom, the first one is Slack, pure Slack. So it starts, as we have seen, you receive a new route advertisement, you do that. Duplicate address detection, right? So you are sending a neighbor solicitation for yourself. If there is no entries for the address A1 in the device tracking table, I am adding it there, in first line. If there is already one, test an attacker will see it later. Host number 2 is sending a request to a DHCP server. The DHCP server reply with an answer, in this case 2 addresses. Because there's a difference between DHCP v4 and v6. DHCP v6 can reply with multiple v6 addresses if you ask for. So now I'm adding address 21, address 22 for the same MAC H2 on VLAN 100 on port 2. Pretty much like you are doing with DHCP snooping for v4. What's also new? Host number 3 was not doing that, was not doing DHCP, or it's been running for hours before the switch comes up to life, and has done it before. So the switch has no clue. What is he doing? He's doing data recovery. So I've never seen those source address A3 and SMAC. I have 2 options, and you can do both. DHCP list query. Basically, I'm asking the DHCP server, hey, who is using this IP address? Okay? And the DHCP server will say, hey, this IPv6 address is this MAC address. And then I can put the information in the table, right? Or you are simply sending a neighbor solicitation. You receive a traffic from an unknown source. You send a neighbor solicitation for this source, and hopefully you will get a single entry, a single reply, and then you put the information into your device tracking table. If you receive 2 replies, that's an attack, right? And you drop it. Yep. Shout.
Wouldn't the reply from the DHCP would be DUID instead of MAC address?
So with the, you've been in my session before?
Yeah.
Okay, that's good. So the gentleman question is that would the reply from the DHCP server don't be the DUID, device unique ID, which is not the MAC address. It will include the DUID, but also the MAC address. This is specific for this query. And stay for a while on tune to this. Next slide is about this. So if the NA comes back, put into the table. You can add other stuff in this table. Static configuration. Right? If you know, like, DHCP snooping, you can say, this IPv6 address is on this MAC address on this port. You can do it statically. And what is DHCP disk query? You can have a look about those two RFC, one for IPv4, one for IPv6. It's basically not for first-hop security, but it was more for cable modems. Right? If you're using a cable modem at home, the concentrator receiving all the cable modems headend, the CMTS, if it crash, it lose what's associated for the V6 address or the V4 address and the MAC address of the cable modem. So the only way was going back to the DHCP server to get all this information. And indeed, DHCP disk query can get DDoID, but can get also the other information. For instance, there. In addition, there is another column called preference, which is basically the preference or the trust level you can get. If you have a port which is using .1x, it's higher priority, for instance, than the port which is not using .1x, because typically you trust your user. DHCP is typically more preferred than DAD, because DHCP is kind of trusted, right? And so on and so on and so on. So, how do we use it? One entry my device tracking table, host one, a switch, another guy. The other guy sends this unsolicited node, neighbor advertisement, with the address of H1 and the MAC address which is on. So, is the address already in the table? If no, install. Remember, when somebody good is doing that, this is how we learn and add the table. So if the address is not in the table, that's a good guy doing that. Okay, is it the same anchor? And by anchor, I mean, is it the same MAC, VLAN, and port? If it's the same place, yes. That was simply somebody refreshing. So I refresh the entry, because of course the entry in device tracking table timeout, right, as you are running out of memory. If it's the same different anchor, I compute the preference and I compare. If the guy on the left was, I learned it by DHCP, and the guy on the right is doing that, DHCP wins. So I'm dropping. Okay? If the guy on the right now is doing .1x and the guy on the left was not, the guy on the right is the right guy, right? So I replace. If it's the same, I will check now whether the host one is still alive at the anchor. So I will be sending an explicit neighbor solicitation, unicast now, not on all the VLAN, right? Just on this port to check whether it's still alive. If it's still alive, not moved, I drop the request from C. Else, I replace. It simply means now that host one is moved there, right? Change access point, for instance, because it was roaming. And for instance, in this case, we can see the bad guy is there. And an example where there's a theft. Okay, is it, the address is already there? Yes. Is it the same anchor? No. Compute the preference. They are the same. That. Is H1 still alive on the previous port? Yes. The second one, no. You claim to be H1, but I know H1 is still alive there. You pretend that H1 moved there. No way, because it's still there. Okay? I drop. And this one is basically what I've explained, where the difference between the preference are lower. The newer attack has lower preference than the original one, so I'm dropping it. And the last one, if you follow, this is what I said. H1 is moved to another port or to another access point. So it's the same address, different anchor, same priority. It's no more alive, so I replace it. So it's not rock solid, right? We can imagine scenarios where by race condition it does not work, but it's way better than anything, and this is what you are doing with DHCP v4 snooping, right? it's way better than anything else. Example, here we are using device tracking policies. It's no more regard policies, right? Device tracking policies. And having multiple things like you can have limit address, trusted port, but what's really important, this is the security level. It can be clean. I am simply collecting the information I get, build a device tracking table, but I don't use it. Could be used when you start, right? To be sure you don't make a mistake. To see whether it's populated correctly, everything works fine. The list query, for instance, work. And then you may want to do inspect on the ports facing your client, like the Wi-Fi. Right? Inspect. Inspect means I am gleaning the information, collecting the mapping, but if you are sending an NA which is wrong, I drop your NA. It will not go through. Okay? You can jump it to guard. The bottom line, it's like inspect, but it will also block DHCP and route advertisement. Okay, some demonstration. Same thing as before. I have a server using Café : 80, a switch, normal host, and the VLAN. Again, all of them being Cisco routers because that's easier for me to do it like this way. To go faster on the switch, I will immediately configure the device tracking policy and apply it to all the ports. So conf-t, created a device tracking policy node. Security level inspect at the bottom, right? I will be blocking the attack. I am gleaning, but also blocking. Device role node, you see in protocol DHCP6, protocol NDP, I could have added DHCP4 and ARP. Data glean, recovery NDP, this is when I don't get the entry, I am sending a neighbor solicitation. I was lazy in my setup, I could have added list query, right? But that's what it means there. And I limit the address count to 10, because there are some attacks where people are trying to overflow the neighbor cache by having thousands of entries for a single MAC. I limit here 10 IPv6 addresses per MAC addresses. Apply the policy node to all the VLAN. And if I look about the content of the device tracking table, empty, right? No traffic. Right? You would have a Windows machine would be full because they are very chatty. Same thing for Mac, right? Sending MDNS information, but here, Cisco routers don't send useless traffic. Host. I'll bring the ping to the Café : 80. Let's have a look at the neighbor cache. And we have basically two entries. The global address linked to the MAC address of the server, right? Currently no attack at all. If I look now in the switch, which is the content of the device tracking table, I learn both the link local and the global of the client and the server, right? Because they had to each exchange traffic to both directions. And look how did I learn it? NDP. Could have been ARP, DHCP, and so on, right? But it's how I learn it. And the MAC addresses are there. Let's go to the VLAN. The VLAN will configure itself with a bad MAC address, right? You will see it. Oops. Bad. So it's easier for us to see what's happening. Disable that, right? Because if the bad guy was behaving correctly, it will detect a duplicate address and stop. So I need to disable that. And the address is the address of the server. Okay. And what I will do as well, I will enable debugging of the NDP traffic to see whether it's receiving neighbor solicitation and neighbor advertisement. Back to the host, I need to clear the neighbor cache to redo DNS NA. Right? I will be using the correct information. It's empty. Redo the ping. Success. If I go to the VLAN, he has indeed received the NS, right? Received the NS for itself. He sent the neighbor advertisement, sending NA, but it has been blocked by the switch. And indeed, if I go to the switch and I look now at the device tracking table, I got only one entries, but the entries cafe 80 is still the good MAC address. I have refused to learn, right? Because the other one was still alive, right? It was not moving. It was still alive. I sent a neighbor a solicitation and got it. The only new entries is FE80::, bed, because the link local address of VLAN was not protected, was not used by somebody else, right? So it's a valid one. And on the host itself, the neighbors is the right one, because it never received a neighbor advertisement from the bad guy. So all is good. So once, yep. Yeah.
Is 10 like a real-world example? What's good to use, and goes it into error disable if it exists?
Yeah. So the question was about the amount of what should be the default number of maximum v6 addresses per MAC addresses, right? In the example, I use 10. I think that's correct because you have the link local, and typically on Windows machine, you keep 8 other v6 addresses plus the link local, make 9. And if you are using CLAT 6.4, right, for IPv6 mostly, for example, that's another one. Make 10. Now, make it 20 if you prefer to be on the safe side. It will not have a big impact, but not put 3, right? That's basically my point. So one issue with flag and Android device, for instance, they don't have DHCP, and having DHCP v6 would allow for a more trusted center of truth, right? Source of truth. So there is a way, for a little bit more than a year now, to use DHCP v6 to report which Slack address you are using. So you don't use DHCP to get a leased address. No. You use a random interface ID, and you report to the DHCP server which IPv6 address you are using, together with your DUID. So no authorization, somebody can lie, and as far as I know, there is nobody doing it. Other topic, and I forgot to chocolate for the gentleman. Sorry. Dangerous, right? You see why a bottle of beer would be too dangerous there. Address availability. DAD. Okay, so if you do all the ARS, array, and blah, blah, as you have seen, including in my hotel, right, you are sending neighbor solicitation, basically a DAT, duplicate address detection, and you hope not to get any reply. If somebody else was using the same IPv6 address, he reply, of course, with a neighbor advertisement, and then, yeah, you're stuck. You cannot use this IPv6 address because it's already used. Okay? It's pretty rare. Can happen in the lab if you are doing it, everything manually, of course. Again, no authentication. So the bad guy, right, is there to see array, arrays, and blah, blah. The good guy, the victim, is doing that. And of course, the bad guy reply, hey, I am address C, right? But I don't care, I reply, I have address A. The guy cannot use it. He goes back to sleep, right? Actually, if he's using temporary address, he will try 3 addresses in a row and stop. But of course, the bad guy will do 3 times the same attack, right? So how can you do this? Simply device tracking table again, right? So if the attacker tries to do it as the first one, A, we trust it. We always trust the first speaker. The A on the left was the first one trying to use address A. We trust it. If somebody else was using address A already, we will signal it as well to host A. Okay? So that still works. That will be done by the switch itself. It will send the NA, right? But in this case, the NA is coming from somebody else, and no way, right? So we block it, pretty much like we've seen before. We can do it pretty much like in the IPv4, same thing. We can pretend, the attacker can pretend to be a DHCP server. So when the client, let's say a Windows machine, wants to use IPv6, and he sends a solicit on the nodes for v6 address, the good guy in green reply, in this case with a DHCP relay, and the good guy reply, the bad guy reply in red. There are preferences. The bad guy will pretend to be the best one, preference to 55, and the other one using the default 128. Now the victim asks, hey, I confirm, there's always a two-phase commit, right, for DHCP. I confirm I really want this one, and then he reply, hey, no more available, sorry. Or he reply with an address which is completely wrong, a bogons, an address which leads nowhere. Again, pretty much like in the IPv4, right? And the mitigation is exactly like in the IPv4, and pretty much similar to our regard. You know where the DHCP server is because you are the network operator. So whether you deploy via an access control list or DHCP guard, I know the story right now. Attach a policy to a VLAN and so on. So the solicit will indeed reach the DHCP server. He can reply with the advertise. All is good. If the bad guy wants to send an advertise for an address, it hits the DHCP guard, and packet will be dropped. Meraki, the access point, enable DHCP guard, and notice it's not DHCP guard for v4, DHCP guard for v6, it's DHCP guard totally, right? Which is cool. In the switch, last time I checked, you need to use an access control list for doing this. Okay, the last remaining part is that a neighbor cache or an ARP cache, let's say in IPv4, if you're using a /24 your network, the ARP cache can have only 256 entries, right? Actually 254 because there is a 0 and the old broadcast. Every router can have this cache filled with bogus entries. 256 entries in ARP cache, it's easy for any router. Now, in v6, there's a /64. So on paper, a neighbor cache could contain 2 to the power of 64 entries. And no routers on Earth can ever have a memory large enough. So, what if a bad guy, let's say we are Netherlands, and somebody, let's say from Australia, want to scan this IPv6 network in the conference? It scan colon A, right? And then colon B, and then colon C, and so on and so on. It arrives at the router here. Well, there are firewalls blocking it, but assume we don't get a firewall. It fills up the neighbor cache with incomplete entries, of course. And we are sending neighbor solicitation over the Wi-Fi here. And again. At some point of time, the neighbor cache, we have a 3-second timeout to clear it, is filled. We cannot add new entries. No, that's me in my hotel, right? or you in your hotel, and you want to access this network here, you are valid use to a valid server. Guess what? Your package comes here, right? TCP SYN arrives here. There is no entries in the debug cache. We cannot add an incomplete entries for your destination because it's already filled. Because the attacker continues to do it, right? All the time. So no communication. How to mitigate this? We use a neighbor cache, the device tracking table in the router, cleaning as before. No more on the switch, this time on the router. And all the scan from the guy from Australia, we apply this mechanism. This is called destination guard. And do I have an entry in my device tracking table? Have I seen traffic from this address? If yes, we continue. If no, we drop. Right? So traffic to destination that I have never seen on my device tracking table are blocked at the router. We do not send neighbor solicitation for it. Some more information. A lot of logging can be done. In this case, you see in the log SISF. This is the engineering name of First Stop Security, which is more the marketing name. It stands for Switch Integrated Security Features. A lot of things you can see. A is for the address, P is for the providence and the priorities. You get the MAC address and so on and so on. And the VLAN in this case is V. Pretty condensed. Many V6 features, right? First Stop Security. Array guard we've seen. Device tracking. This is basically the core of everything. DHCP guard, decision guard we have seen. But we have also source guard. Device tracking only blocks the NA from the wrong address. It does not block you spoofing an address. You can send packets from another V6 address, right? You will not receive it to the destination, but you can still send it. Okay? So if you want to block this, this is source guard. Prefix guard is mainly for service provider CPE, where you use DHCP prefix delegation, PD, to allocate a /48 to one CPE. And you ensure that all the traffic coming out of this CPE is within the prefix that you have been delegated. Array throttler is basically an access point. If you configure your router to send array every 5 seconds, it's a multicast over Wi-Fi, and multicast over Wi-Fi has a huge penalty hit on the battery life. Right? You know this by now, I guess. So we simply reduce it, kind of stupid stuff. And we can as well suppress multicast, because the access point or wireless LAN controller knows which are the member of the multicast group. And in some case, neighbor solicitation, for instance, he knows exactly the single unicast address, right? So he's sending to unicast MAC address. So it's no more multicast, saving the bandwidth and the battery, and so on. As I explained, I'm running this session with different set of slides, of course, for more than 15 years now. At the beginning, this was the roadmap, right, for all the devices and all the features. And in the beginning, there were a lot of red and empty spots. Now everything is green. So it's pretty well available. Now, some features are not available. For instance, array throttler is not available on some platform that do not have Wi-Fi, right? That makes sense to have them there. The spots are basically useless feature. Talking about roadmaps, software-defined access. You know there are layer 2 and layer 3 overlays and underlays. A layer 3 overlay, this is when your fabric looks like a routed network, and what you are doing, all the fabric edge, the 3 routers at the border, basically transport IP frames, right? IPv4, IPv6, or both. A layer 2 overlay is basically the 3 fabric edge switches. And what they transport over the underlay is layer 2 frames, right? Internet frames. Could be IPv4, could be IPv6, could be whatever. But we'll focus on this one. First off, security. This is within the LAN, not over the internet. For an SDA fabric, right, we have a lot of devices, a controller, because this thing must be controlled to see what's happening. We have routers called fabric edge, which are no surprise at the edge. And we have core routers in the middle, connecting all the fabric edge. Of course, not really like this topology, right? Something more optimized. All the set of core and fabric edge are the underlay. Could be running whatever you want. What you define now with the fabric edge, and specifically the port facing out, is the overlay. You know this, right? And what you add are endpoints, EP, which are basically the Wi-Fi access point, your host, your servers, and so on. A specific set of endpoints and fabric edge are defined what we call a VLAN. Okay? You group them by VLAN. Basically, what you are doing is splitting a normal switch in a distributed switch, and that's it. Encapsulation is typically in VXLAN, so UDP, and in least with user control plane. But does not really matter here. Okay. Typically, within the layer 2 overlay, the router will be in the fabric, right? That's the goal. The router will rarely be outside of the fabric, the router to the internet, I mean. So by default, all traffic at the fabric edge are using array guard and DHCP guard, blocking every user connected, or every endpoint connected to a fabric edge to send arrays. And look about this. If you look about all the policies in an SD access fabric edge, you will see notably this one, which is enabled by default. That is exactly what we have shown in the demonstration. You see other stuff, right? Gleaning from ARP, gleaning from DHCP, and DHCP, we want a number, is V6, which is cool. Gleaning for DHCP 4, neighbor discovery. MAC address 12, so I suggested 10, they are using 12 here to be sure. 4 IPv4 address per MAC, which is very strange. And security level guards, right? Meaning I will block, not only I'm gleaning the traffic and blocking wrong NA and wrong ARP, but I will also block arrays and DHCP. So for instance, we have on the controller the device tracking table, which has already been done. We have different endpoints, right? Endpoint 1, endpoint 3, and so on. And now, and the endpoint 3 has got IP address 1. Endpoint number 1 is doing DAD. And in the title, I put IPv4 v6 because it's exactly the same. So it's doing that via ARP request or neighbor solicitation. Fabric Edge compute the preference, .1x, DHCP, and blah, 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 blah. Okay? It check whether we have IP1 somewhere. Yes, we have it in Fabric Edge number 3. So I am sending over the underlay a duplicate address request to the Fabric Edge 3. It's distributed, right? So you need to pass the request. Fabric Edge 3 send an ARP or a neighbor solicitation, right? Again, we'll do the same thing to endpoint 3. Who is doing IP1? Endpoint 3 will reply, yes, I still have IP address 1, so I'm sending with a neighbor advertisement or ARP reply. Okay, you understand this? I compare the preference, DHCP blah blah .1x and so on. And then, in this case, I am sending a duplicate address confirmation, right? I syslog this, both of them, because something is unusual, most probably misconfiguration, right? Don't take me wrong. And then I'm sending an ARP and a neighbor advertisement from the Fabric H1 to the endpoint 1. So basically, we are transporting the traffic NS, NA across the fabric, and we are logging more. That's basically it. We can use it as well for something interesting. Assuming that we have traffic between endpoint 1 and endpoint 2, right? And then we will see that binding table and everything is okay. But now I use my PowerPoint magic, right, to move endpoint 1 and roaming to another access point. Oh. Then Fabric Edge 3 will say, hey, endpoint 1 and MAC 1 is now at Fabric Edge 3, even without traffic, right? Because it's associated at the MAC level. Then the controller will say, hey, I see the MAC moving, delete the entry for endpoint 1 in Fabric Edge 1, add endpoint 1 with those IP, because device tracking table has got the IP, to the Fabric Edge 3, they are added, and then the traffic goes, right? This is how you are roaming. So you can use the binding between MAC addresses, because you know the MAC addresses when you do roaming, there's only the MAC address, see that is first noun before the IP traffic, IP, access point, a lot of things there. So we spend 1 hour and 20 minutes on first hop security, but what is beyond? Can we look beyond this? And yes, right? There are other stuff to do. And this is basically my session on Tuesday. You can listen to it on the recording. You can do anti-spoofing. You need to get infrastructure ACL, protecting your traffic from the outbound for some specific extension headers, for instance. Routing security, yes, you need to secure your ERGRP and your SPF traffic with authentication, like you do with IPv4, no surprise. And the good news that all your VPN firewalls IDS support v6. Again, I'm doing this for 15 years now. At the beginning, ask your firewall vendor whether it supports v6. And yes, no, right? Everyone does it. Last word about MAC addresses. Remember I said somewhere, the v6 addresses change, right? And we can have 10 or 12 v6 addresses per MAC address. But something is maybe coming. That's a project at IEEE called 802.11bi, where, for privacy reasons, the MAC address can also change. So it's already the case in some place, typically iPhone and Mac OS by default. When you change SSID, you change your MAC address. But once you are associated to one SSID, you stick to the MAC address. At some point of time, some people wanted to do way further and do like we do privacy extension v6 addresses, changing every day or more, having privacy extension MAC address, so changing every day. Which is a little bit more annoying because if you are using, for instance, a captive portal and you have all of the traffic based on the MAC address, good luck, right? My understanding is that project is only done now when you change SSID, which is okay. Right? It's a good feature. Summary. Obviously, NDP and DHCP v6 are different than IPv4. The main difference is basically the use of Slack. But the common approach works for both, right? The device tracking and the area guard and the DHCP guard and so on. Again, trusted device, this is your access point, this is your switch, your router. You protect them because your security relies on them. And you know how they are attached on which interface. So you can really say, those are trusted port and the other one are non-trusted. Access point, it's easy. All the Wi-Fi access part is, of course, untrusted, and everything which is right upstream should be trusted. Now, the bottom part is really important. right? For a few of you that say, hey, I don't run IPv6 in my network, which I call you the liar with a big smile, you are running v6, you should already deploy device tracking and array guard at least on your v4 only network. Maybe this is the only v6 feature you will be deploying. This is array guard, but it will be enough and good already. Okay? You may even be surprised about what's happening there. More information. So I wrote a book on IPv6 security. It's more than 15 years old now, but still very valid. I was also already explaining the mapping over there. Another book was about LAN security, which was more about spoofing and DHCP snooping. Couple of RFC, and if you see, no surprise, a lot of the authors are coming from Cisco systems, right? The one there, Eric Levy-Amignoli, is the chief engineer who coded all the device tracking, for instance. Very nice guy. You notice surveys. We love surveys, right? It's important for our ego, of course. We like to get good score. There is a competition among speakers. But the most important thing is to write in the session what was good, what was less good, right? What keeps missing, should be shorter or longer. Very important. As a speaker, I read it, but I am also responsible for the IPv6 track in the US, and we are seeing something which is missing. We may change the content and request the content. That's really, really, really important for us. And we do read all the comments, just to be sure. I ask any speaker, yeah. First things we do every day in the morning for 1 week is to check this. That's really... Okay, this is the session. On-demand library for the session on Monday and Tuesday. All right, booking a media engineer, that's maybe a little bit too short now. This was all the session regarding IPv6. There are still a couple of them, including Nathan, can you stand up? So tomorrow, if you don't know IPv6, Nathan is running a fantastic IPv6 : it's not a typo, right? It's happening. It's more like a basic training though, right? So if you understand everything I said today, maybe, sorry, Nathan, listen. And of course, enjoy IPv6 here. If you noticed the way we are doing the SSID, it's very strange. You don't have, if you're using an iOS phone, an Android phone, you don't have any IPv4 address, but you can still access any IPv4 website. Okay? It's called IPv6 mostly. We're doing it for the second year. Works perfectly fine. With this, I can say, take some question in the room after, because we are running out of time now, or actually just on time. Thank you so much for your attention, and see you at the celebration later today. Thank you.